previous lectures, we have discussed three different levels of material structures, such as atomic level, crystalline structure, as well as microstructure of materials. And we outlined the general idea of the whole course. We at least try to show you how the different level of structures control different types of material properties. The next very important part of this course is actually to show you some examples of some material science techniques which can be used in order to see these different level of structures. In these specific lectures, we will talk about transmission electron microscopy, which allows just exactly to see atoms, to analyze the atomic structure of materials. And we will spend some time in order to understand the general principle of transmission electron microscopy. Again, our famous screen, scale of structure organization. And so what we will talk about here of the level of structures and the order of angstroms. So which correspond to atomic structure, and specifically from this table, if you wish, we will discuss the material science technique, characterization technique, named transmission electron microscopy, or TEM. So a little bit about the history of TEM. So the first TEM was actually designed and built in 1931, and on this screen you can see the first TEM, and at some point one of the developer, Ernest Ruska, he got a Nobel Prize for this type of design. Of course, as I will show you on the next slide, there is no any comparison between the historically developed first transmission electron microscope and the current advanced type of electron microscopes. However, idea is the same. You are using electrons in order to define the fine structure of your materials. So now the question is, so why actually electrons? So in order just to give you just very brief insight, I want to refresh your mind that actually electron or every particles, they may behave as a particles or as a wave. And so this hypothesis, which was suggested by Prince Louis de Broglie in 1924, it's brilliant, of course, hypothesis, which was then very rapidly experimentally proved, was that indeed electron may behave as a wave, and if it's so, then so have a pretty high acceleration, and the acceleration voltage in the typical TEM microscopes is on the order of 300 kilo-electron volts. So if we, let's say, accelerate our electrons to very high velocity, which is close actually to the speed of photons, so then we can obtain the waves with extremely low wavelengths. And we can use these waves in order to investigate the material, for example, structure, similar as we are using X-ray in order to investigate the crystal structure of material. The difference is that, so because the velocity of electrons is so high, so the typical wavelengths of these electrons can be on the order of picometers. And you know that resolution of this type of diffraction technique is related to the wavelengths of the used waves. And indeed, if we do have picometer wavelengths on the accelerated electrons, we can expect extremely high resolution on the order of picometers, which is much, much less even than the size of atoms. So do we have it? No, we don't. And the reason is that, again, so same as in crystals, we don't have the perfect, let's say, lenses we don't have the perfect systems which allows us to use these advantages of extremely low wavelengths of electrons. We do have a lot of imperfections. And I will briefly will note this type of imperfections of the scanning electron microscope, but because of this imperfection, the current reached resolution at TEM microscope is still very high, but not on the order of picoseconds, but on the order of 0.7, let's say, angstroms. No, let's say 1 angstroms. So it means with the resolution of 1 angstrom, which is more than enough in order to see and try to understand the atoms in our materials, so this resolution can be reached with the help of transmission electron microscopy. So what kind of imperfection I'm talking about, just very briefly without big details? First of all, we are talking about spherical aberrations, same kind of imperfection as you can find in the optical system, but in the electron microscopy we do have also lenses, and however it's not the optical lenses, it's electromagnetic lenses, but all these lenses do have same type of imperfection, and spherical aberration so doesn't allow us to go to picometer type of resolution in the microscope. Idea is very simple, that electrons which are coming to the lens slightly further from the X of the lens will interact inside the lens differently as compared to electrons which coming closer to the walls of the lens. Because of that, instead of 1 point, we will see some kind of circle on the screen. So the other imperfection is chromatic aberration. Again, you should know this type of imperfection for the optical lenses. The general idea is the following, that so whatever we have, we cannot make all electrons have absolutely same energies. Still, even in the very good, nicely designed system, we do have some energy distribution, and you can imagine that electrons which do have slightly different velocity and energy when entering, the focusing system in the transmission electron microscope will bend or focus slightly different to those electrons which have lower or higher velocity or energy. Because of that, again, instead of point, you will see some kind of circle on the screen. So finally, I should mention one more imperfection, which is astigmatism, and it just means that electrons which focused on 2 different planes can be focused differently, and again it leads to the final conclusion that up to now, with whatever characters which were designed and built recently, the maximum resolution which we can reach with the help of the transmission electron microscope is on the order of 0.7 angstroms, which is still very good. On this slide, so you can see some characteristics of one of the popular TEM, so Titan 80, so which is manufactured by the US FAI company. And again, so you can see that accelerating voltage here on the order of 300 kilo electron volts, and that so resolution which you can reach here is just on the order of 0.1 nanometers. So it's equipped with different diagnostics, and that we will talk about. So the next topic which we'll discuss, what actually is going on when the electron beam interacts with the surface, with your sample. First of all, because we are talking about transmission electron microscopy by the name, you can imagine that in this case the electron beam should pass through your sample, and all detectors which you can imagine are just positioned below your sample and grabbed all information which showed up as the result of interaction of the electron beam with your sample. So it means, of course, it's a special field of science if you want how to prepare the sample of thin enough in order the statistically enough number of electrons can pass through. So just want to mention the typical size thickness of your sample should be less than 100 nanometers, and in some sense smaller is better with some exemptions, but we will not discuss them today. So now the electron beam is passing through your sample. What is going on? What information we can obtain? Now, first of all, of course, we do have some backscattered electrons, and in principle they can be analyzed, and as we discussed in the lecture dedicated to scanning electron microscope, this analysis provides very useful information about the elemental composition, if you want, of your material. However, it's not the case for TEM, so we do have some electrons which pass through your sample almost without any changing of direction and energy. So that's part of electrons can be analyzed by special detector. So we do have also electrons which pass through, changing significantly its direction without big change of energy. Also, we do have electrons which significantly change energy while passing through the sample. Finally, so as the result of interaction between electrons and atoms, some kind of photons showed up, and the energy of these photons can be analyzed and also will provide us information about the chemistry of our material, which we will discuss in a little bit more detail in the next slides. So we have to also explain here qualitatively that because electrons, as you know now, can behave as waves, so and the crystal structure of the material, again, as you can imagine, with interaction of this electron can provide the diffraction of these electrons, so you can obtain the diffraction, if you want picture, image of electron diffraction of the crystal structure of your material, which will provide extremely useful information about the crystallography of your material, specifically about crystal orientation, crystal lattice parameter, and even specimen thickness. So let's go one by one, try to explain what kind of TEM imaging modes you can get. First of all, we are talking about so-called bright field image and dark field image. If you read any kind of article where the TEM analysis was used for the characterization of your material, so everywhere you will find out this abbreviation BF and DF. So, and you have to understand what does it mean, and I will provide you this the direct explanation on the next slide. But so it means that, so in first case, in the bright field image, the detector detects only electrons which pass through without losing energy and practically without changing the direction of their propagation. So in the dark field image is vice versa. We are detecting electrons which is passing through without changing energy. Again, elastic kind of interaction, but with significant change of direction of initial movement. Also, we can get image when we are using the interaction between the elastic and non-elastic type and diffracted beams. So these transmitted beams, TB beam, and diffracted beam, DB beam, and this will give us the lattice images. In some sense, gives us information about the atoms inside your material. And finally, as I mentioned, the diffraction patterns, and you can obtain images. Diffraction patterns will provide us information about the crystal structure of our material. So this screen is very important in order to understand and provide the right interpretation of the obtained images, TEM images. So what we can see here, so we do have actually gold particles spattered on the carbon substrate. And on the left, we do have the dark field image of this particle. On the right, we do have bright field image of this particle. Now let's start with bright field image. In this case, we do have the incident beam passing through our sample, and we are monitoring only the transmitted beam electrons which pass through without almost no change of its initial direction of propagation. So in this case, you can imagine that through gold, because it has much more high density than carbon, much less electrons will pass through as compared to the carbon substrate. And because of that, on the image, you can see that gold particle looks darker than the carbon substrate. On the left side, we do have so-called dark field image when the diffracted electrons were detected, the electrons which significantly change its direction as the result of interaction with our sample. And again, it's clear that much more electrons will change, will diffract from the or in the vicinity of the gold particle as compared to extremely light carbon particles. That's why on bright field image, the gold particle looks much brighter. On the dark field image, looks much more brighter as compared to the carbon. So that's understanding of the physics of interaction between the electron and particles is very important to provide the right interpretation of the obtained results. Put your attention that so in the scanning electron microscopy, in backscattering electrons, we will have the contrast which is similar to the dark field image and not to the bright field image. And again, so typically, so it's nice to have both images of investigated sample before you go to more quantitative type of analysis. Again, if now we try to obtain image taking into account transmitted and diffracted beams, we will go to so-called lattice imaging mode. And in this lattice, for example, on this screen, you can see 3 grains of nickel aluminide. And you can very nicely also see the grain boundaries, and you can see different type of defects, dislocations, and even in some sense you can see atoms, and you can measure in principle the distance between these atoms and make a conclusion about the crystal structure. So lattice imaging, it's atomic scale of imaging, and provides you information about the lattice structure or even atomic arrangement in your sample. So the major contrast mechanisms, it's very important to know that so there are 3 main image contrast mechanisms there, and because very often all 3 of them work together, it's very difficult to provide the right interpretation of the obtained results. Because of that, so typically, or you have to work very closely to the expert in the field of TEM in order to understand obtained results, or to go deeper by yourself to the physics of different type, which leads to the different type of contrast mechanisms. Let's just briefly outline them. One is so-called mass thickness contrast, relatively straightforward, as we discussed for the bright field image or dark field image. So, so much higher Z or atomic number of elements, or the thicker sample you have, so less transmitted electrons you will detect, and more reflected or diffracted electrons you will see. On the other hand, and this is more or less straightforward and understandable, but on the other hand, you also have to account so-called diffraction contrast. Diffraction contrast is the different type or density or scattering of transmitted beam as the result, for example, of their interaction with different type of defects, such as dislocation, grain boundaries, which I showed you already. So that's why it's very important to understand the existence of this type of contrast. And finally, as for me, the most complicated type of mechanism is so-called phase contrast. So this the interference between the transmitted and diffracted beam, as I showed you in the case of the lattice imaging, which provides you somehow information about the atomic arrangement of your sample. This so-called high resolution TEM images. And so when all these 3 mechanisms work together again, sometimes it's very difficult indeed to provide the right interpretation of the obtained results. Finally, I want to mention about one more TEM mode, so-called scanning transmission electron microscopy mode, or STEM mode. This mode is widely used for the scanning electron microscopy, but relatively new in the case of the TEM. It's not classical TEM mode. In this case, we focus the E-beam to extremely fine probe on the order of 1 angstrom, and then we scan this probe along your sample, and so the transmitted electrons as the result of this scanning can be also detected as the brightness of pixel on the screen in so-called STEM imaging mode. There is some advantages and disadvantages of this mode, which you can see on this slide, but we are not going to very big details, just only to mention that if you want to combine the TEM with some other chemical diagnostics, such as energy dispersive spectroscopy. Typically, so you're doing this type of spectroscopy by using scanning transmission electron microscopy mode. So finally, several words about the diffraction. It's a very important part of the TEM analysis. Again, if you hear this term diffraction, you have to imagine that in this case we can obtain information about the crystal structure of our material, absolutely the same way as we can do for the X-ray diffraction analysis. However, the difference is here that we are using electrons and not X-rays as the waves in order to provide the diffraction image, and for this reason, of course, the resolution of the electron diffraction analysis is much less as compared of the X-ray diffraction. So if you remember, in the X-ray diffraction, typically again for the standard one, so you need to have your sample on the order of at least square millimeters and depth around 100 microns. So here you can go to resolution on the order of, let's say, 1 nanometer, trying to provide information about the crystal structure of your material. So again, what information can be obtained with the help of the electron diffraction. First of all, you can conclude, so do you have amorphous material? This image of diffraction, that is fuzzy picture of diffraction, you can see on the upper left corner of the screen. Then you may conclude that maybe it's crystalline material and polycrystalline material. In this case, you will see the rings, and you can measure the diameter of these rings, and based on this information, you can then obtain the data on the despacing of this crystal structure, or you may see several spots which will indicate that you have the monocrystal, single crystal in your view, and again you can obtain information about the parameters of this single crystal. Again, so just very briefly, so indeed if you do have polycrystalline material, for example, you can measure the diameter of these rings, and then knowing diameter of these rings, which is R, on this screen, as well as knowing the wavelengths of electrons and characteristic parameter of this microscope L, you can then calculate the despacing, and knowing despacing, you know how to define absolutely same way as we are doing for the X-ray diffraction to define the crystal parameter of the investigated phase. So in addition to the considered mode, again, we can make some chemical analysis in the TEM mode. Specifically, similar to those we can do for the scanning electron microscope, we can use energy dispersive spectroscopy analysis to get information about the elemental composition in the investigated sample. So idea very simple. So we have electrons which interacts with atoms. As the result of interaction, so the ion showed up, and then the electron from the outer shell will come to the lower shell, and the photons with very specific energy, specific for this element, will be emitted, and So the detector allows us to analyze the energy and the number of electrons emitted, and based on this analysis we may conclude what elements, not phases, what elements do we have in this spot. So, so here I want to outline that again the resolution of this method, EDS method, for the TEM is very different as compared to the scanning electron microscopy. If you remember, in the scanning electron microscopy we analyze the volume on the order of microns. So here we can get information from the volume on the order of cubic nanometer, and that's why it's much more precise. Element distribution can be obtained from your sample in different mode, in the mapping mode, in the scanning mode, in the spot mode, and so on and so far. Again, for example, with the step distance of 1 nanometer, you can scan the distribution of iron and titanium on the sample showed on this screen. And at the very bottom, to get the, I want to say, semi-quantitative information about the elemental ratio in the analyzed spot. So finally, one more chemical analysis technique is available, so-called electron energy, electron loss spectroscopy, EELS. So it's also relatively new, and idea is absolutely same as in the case of the EDS, as in the case of energy dispersive spectroscopy. However, in this case we measured the energy of electrons which interacts with the atoms in the investigated sample, and owing to the different type of interaction, the plasmons or some other type of interaction between electron and atoms. So the electron, they lose energy, and we measure the specific energies which were lost by these electrons, and this energy corresponds exactly to the elemental composition of your sample. So why do we need EELS? Why EDS is not enough? So different advantages and disadvantages of EELS exist. It's a little bit more difficult to interpret the obtained results for EELS. However, so EELS provides you information not only about the element itself, but also provides you information about the valency of this element, which can be extremely important for the analysis. For example, on this screen you can see the EELS edges, energy loss edges for the different materials where titanium is in different modes, and based on that you can even decide, so do we have titanium oxide, titanium, or it's some more complicated, let's say, perovskites here. So indeed, so information about the valency of the investigated elements is a unique feature of EELS. Also, EELS is more sensitive to the light elements, such as oxygen, nitrogen, boron. So, and for this reason, if the light elements are the topic of interest for your in your sample, so I can recommend to use EELS instead of EDS. So let's conclude. Conclusion is very straightforward. You understand that TEM comprise a range of very different modes, if you wish, which give you so a variety of information about the structure of your material. And in total, in the modern microscope, you can calculate, you can use, actually not calculate, 40 different modes, and they will provide you slightly different type of information about your materials, which includes again imaging, as well as electron diffraction spectrum, as well as EELS, EDS spectrum, and all together. So my recommendation is that you have to understand so the uniqueness of each of this approach, and so it's very often it's better to use different approaches for the same sample, which will provide you more information. However, every time I want to outline that the interpretation of results obtained, of images, data obtained, is very difficult. That's why you have to work together with the high-level specialist, or to go much more deeper in the physics of the TEM. So TEM is a great tool to investigate the atomic as well as crystal structure of the material, and I want to encourage you to use widely this technique in your research. Thank you very much for your attention.